Okay, so this chapter is going to be talking about random variables, and we're still going to be working with probability as we go through this chapter. So let's look at this kind of introductory problem and kind of warm up from here. So what we've got going on here is if we flipped a fair coin 3 times, what is the probability that we get at least one head? So our sample space would be this right here, right? Those are my 3 options that I could get, okay? And so my probability here, each outcome is equally likely. So my probability here is 1/8 for each of those in that sample space. And my variable here, you'll notice it's a big capital X, is the number of heads obtained. That's what I'm looking for, is the probability that I can get at least one head. Okay, and so if I look down here at this table that I have set up for you, I've got my value, the number of times X appears. So X could appear 0 times, which would be this one right here, right? X could appear 1 time, which would be, where is it? This one here, and this one here. Okay, X could appear, and X being heads, remember, I could get heads 2 times, okay, which would be this one, and this one. Or I could get X all 3 times, which would be this one right here. So my probabilities for these, my probability of getting a heads 0 times would be 1 out of 8. My probability of getting a heads 1 time is a 3 out of 8. My probability of getting a heads 2 times is a 3 out of 8. And my probability of getting a heads all 3 times is a 1 out of 8. So let's do a couple of reminders here of what we're looking at here. First of all, is this a good probability model? Remember, a probability model describes all my possible outcomes of a chance process, the likelihood that these are going to occur. So this right here is my probability model. And is this one a good one? Okay, does it describe all my possible outcomes? It does. Okay, 0, 1, 2, 3. It assigns probabilities to them. And all of these probabilities, remember, they have to be between 0 and 1. Okay, and they have to add up to 1. And they do. If I add all those up, 1/8 plus 3/8 plus 3/8 plus 1/8 gives me 8/8, which gives me 1. So this is a good probability model. Okay, and this is my probability, this is called my probability distribution. So when I'm looking at what we call these random variables, this distribution of the probabilities is my probability model. So this is my probability distribution here. So if I want to know the probability of getting at least 1 heads, right? So I'm looking for X being a capital letter here. So big capital X occurs greater than or equal to 1 time. I want to know what that is. So to do that, I'm going to take all of my probability values here that fit this criteria. So 0 times showing up heads, that doesn't fit my criteria, right? Because I want heads showing up 1 time or more. But my heads showing up 1 time fits that criteria. Heads showing up 2 times fits that criteria. And heads showing up all 3 times fits that criteria. So my probability here that I'm going to get heads more than 1 time is 7/8. The other way that I could have done that, right, is I also could have found that by doing 1 minus the probability that X equals 0, right, which in this case would be 1 minus 1/8, which again gives me 7/8. So those are the 2 ways that I could do that. So let's take a look as if we were going to do a histogram with this. So I can sketch this data onto a histogram. So I can do a quick sketch here of 0, 1, 2, 3, 4, and then put my probability values going up the sides, right? Here's 4/8 and here's 2/8. Okay, so if I do a quick histogram of this, I get a probability of 1/8 that they show up no times at all, 3/8 that it shows up 1 time, 3/8 that it shows up 2 times, and 1/8 that it shows up 3 times. Okay, does that look familiar to you? Right? Remember, this is a roughly normal distribution We're still going to have to be able to describe these graphs and what's going on, our center shape spread. So if you need to review that stuff, you may need to go back and look at your notes for that. Okay, so a random variable is going to be a variable that describes the outcomes of a chance process. For example, in the coin toss that we just did, the capital X there was our random variable. The outcomes were how many times that we could see heads. Again, your probability model for this is going to be your probability distribution, okay, like we had done with the table above there. And random variables can be discrete or continuous. If it is a discrete random variable, then I'm talking about a fixed set of possible values, and gaps are going to be in between. For example, let's say I was talking about shoe size and feet. Okay? The size of the shoe is going to be a discrete random variable, right? I either have a 6 or I have a 6.5. There's no shoe size in between. There's no 6.219 shoe size. But if I was measuring someone's actual foot, I could measure 6.219. I could measure 6.374825110. Okay, so a discrete random variable, I'm going to have a fixed set of possible values, where if it was continuous, it would be every single value within that interval. Okay, so when I'm looking at a discrete random variable, the probabilities are assigned by finding all my possible outcomes, just like we did on the last problem. Okay, I found all the possible outcomes that I could have for heads showing up 0 times, 1 times, 2 times, and 3 times. Okay, and I set up that probability distribution. And remember, like we said before, that all my probabilities must have values between 0 and 1, and they all must add up to 1. Okay, remember, a distribution is all my possible values that the variable can take and how often it takes them. That's why my probability distribution here works as my probability model. Okay, let's look at an example of this. So the example here is with Apgar scores. So in 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0-1-2 scale to rate a newborn on each of the 5 criteria. A baby's Apgar score is the sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. So there's no in between here. So these are discrete values. They can't get a 0.75. Okay? They can get a 0, a 1, or a 2. Let's see. So Apgar scores are still used today to evaluate the health of newborns. What Apgar scores are typical? To find out, researchers recorded the Apgar scores of over 2 million newborn babies in a single year. This is something we need to keep in mind for this. We're talking huge, huge data sets. Many, many, many times have these Apgar scores been taken. Imagine selecting one of these newborns at random. So that's our chance process there, doing it by random. At random, to find the random variable capital X equals Apgar score of a randomly selected baby 1 minute after birth. The table below gives my probability distribution for X. So this is the same. So here's my probability distribution here. Remember, this is the same as my probability model. All of these probabilities here should add up to 1, and they are all between 0 and 1. So it makes for a good probability model. So the first part of the question here says, show that the probability distribution for X is legitimate. Well, that's what we just said, right? They all, why isn't it writing? There we go. They all add up to 1, and they are all between the values of 0 and 1. The second part there says, make a histogram of my probability distribution and describe what you see. So as a review, right now, you should pause the video and sketch your quick histogram, and then you can start the video again and check your answer. So your histogram should look something like this. You were also asked to describe what you saw. So remember, you've got my center, right, which has a median around 8. Okay, I've got my shape, right? This one is skewed left with 1 peak. Okay, I have my center shape and spread, right? So my spread, it goes from 0 to 10, with the majority of stuff being between 4 and 10. Okay, and I don't really have any unusual features or outliers. I don't have anything like that. But I've got my center shape and spread described here. Okay. So part C of this question then says that doctors decided that Apgar scores of 7 or higher indicate a healthy baby. What's the probability that a randomly selected baby is going to be healthy? So what you're looking for here, right, is my probability that they have an Apgar score greater than 7. So probability X is greater than or equal to 7. Well, that's going to be my probability of X equals 7 plus my probability. Remember, this is my showing of my work, right? Probability X equals 9 plus the probability X equals 10. Okay, and so when I sub those numbers in, 0.099 plus 0.319 plus 0.437 plus 0.053, pulling them straight off of the data table, I get 0.908. So what that means for my interpretation is that there is about a 91% chance of randomly choosing a healthy baby, because a 7 or higher is considered a healthy baby. So there's a 91% chance of randomly selecting a healthy baby. So let's look at this, another example then. North Carolina State University posts the grade distributions for its course online. Students in Statistics 101 in a recent semester received 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. Choose a Statistics 101 student at random. The student's grade on a 4-point scale with A equals 4 is a discrete random variable X with this probability distribution. So you're given your probability distribution here in the table. Okay, so number 1 asks you to say in words what the meaning of the probability X is greater than or equal to 3 is. What is this probability? Well, in words, what this right here means is that the student got, because this is a B, right? This is an A, this is a C, a D, and an F. Sorry, it thinks I'm trying to change the shape of that picture. So my words here for my meaning of my probability X is greater than or equal to 3 is that what is the probability that a student earned a B or higher? Okay, that's how I put that into context. What is the probability that a student earned a B or higher? And then what is that probability? Well, the probability of X being greater than or equal to 3, right, is the probability of X equals 3 plus the probability of X equals 4. So 0.42 plus 0.26 gives me 0.68, which tells me that the probability a student earned a B or higher in the stats class is there's 68% probability that they earned a B or higher of a randomly selected student. So number 2 says, write the event the student got a grade worse than C in terms and values of the random variable. So what is the probability of the event? Well, the student got worse than a C. So not a C, but worse than a C. So now I'm looking for the probability that X is less than 2, okay, because I want worse than a C. And so if I'm doing that, that's going to be my probability X equals 1 plus my probability X equals 0, which gives me 0.02 plus 0.1, which gives me 0.12. So that is my probability that they got less than a C. And then step 3 there asks you to sketch a graph with a probability distribution and describe what you see. So again, pause it, take a second to sketch and describe, and see if you get the same stuff. So your graph should look similar to this. Your description for it would be your center. Your median is at 3. Your shape is a slightly skewed left with 1 peak. Okay, only has 1 peak. It is unimodal. Okay, and then your spread, being that it goes from 0 to 4, or grades, it shows grades from A to F. Okay, so now let's look at how we take into account the mean or the expected value of a discrete variable. So a discrete variable, this is how I'm going to write the mean. So here's my symbol for mean. This is also the same thing, a capital E parentheses X, the likelihood of so it's my expected value. What this mean does is it takes into account the fact that all of my outcomes are not equally likely, right? It takes into account the fact that some outcomes are more likely than others. So in this particular example, we're going to look at a roulette wheel. Some things that we need to keep in mind with the roulette wheel here is that I have 38 slots on it, and they're numbered 1 through 6. Plus, then I have 1 through 36. And then plus I have 0 and 00. Half the slots from 1 to 36 are red. The other half are black. The 0 and 00 slots are green. A player is placing a bet on a $1 bet on red. If the ball lands on the red slot, the player gets the original dollar back, plus an additional $1 for winning the bet. If the ball lands in a different colored slot, the player loses the dollar bet to the casino. We're defining our random variable x here as the net gain of a single dollar bet on red. The possible values of x are -1 and 1. Remember, this is the net gain. So it's not $2 because I only gain $1. I had to spend $1 to play. And it's a loss of that dollar if I don't win. Okay, what are my corresponding probabilities, and what's the probability distribution of x? So my probability distribution, remember I draw my little table, right? Here's my value, my probabilities that this is going to happen, right? My value is -$1 or $1. Those are my net gain options, right? My probability that I'm going to lose $1 is 20 out of 38. And my probability that I'm going to gain $1 is 18 out of 38. These are not even 1919 because remember I have those 2 slots that are green. 1 through 36, half of them are red, so 18 of them are red. So I have an 18 possibilities of winning, but I have 20 possibilities of losing because of the 2 green ones there. Okay, and so this is my probability distribution and my corresponding probabilities. So the average player's gain is going to be this, and I'm going to be using the formula that is above here. So my probability of the first value, so the first value is -$1, and my probability of that happening is 20 over 38. So I multiply those two, right? And then I'm going to add that to my probability of the second value, times the probability that that value could occur. And so when I multiply those and then add those 2 values together, I'm going to receive, I get -$0.05. So basically what that means in context is that the player loses an average of 5 cents for every dollar they spend betting in many games of roulette. Okay? My law of large numbers is going to tell me that after many repetitions, the mean should start to approach the true mean or the expected value. Okay, so let's do another example with these Apgar scores. So I've brought the scores back up here with that probability distribution for you. Okay, and so the question that we're going to be answering here is what is the mean of random variable x? Okay, and we're going to interpret that in context here. Okay, so to calculate the mean for this, remember my mean is the same as my expected value. Okay, and I'm using that formula that is the x value times its probability plus the next x value, etc. That formula is on your formula chart. When you're showing your work for something like that, so remember these 2 things are the same thing. Okay, when I'm showing my work for something like that, I can start to shorten that, right? Here's my x value, 0 times 0.01 plus 1 times 0.006 plus 2 times 0.007. Once you've written 3 of these values down, you can then do your ... plus your very last one, 10 times 0.053, and that counts as showing your work. You do not have to write all 10 of them down. And when you plug all of that into your calculator, you're going to come up with 0.8128. So when I interpret this in context, what this means is this is my average Apgar score for many babies. Many babies. This is my average Apgar score. Okay? I'm sorry, I put my decimal place in the wrong place, 8.128. You'll notice that this value, this mean or expected value of our discrete variable, does not have to be one of our possibilities. Okay? It does not have to be one of the possibilities. It can be an in-between value. Okay, so let's look at standard deviation and variance for discrete random variables. So we're using our mean for center, so we need to be using standard deviation for spread. Okay, remember our variance is when we square them, right? And our standard deviation is our square root of the variance. So if I'm looking for the variance of a random variable, okay, this is my symbol for it right here. The sigma squared with the capital X dropped down below. Okay, and when I find variance for a random variable, I'm taking my, same as we did before in the earlier chapters, right? Our value, so our value minus the mean, square it, but this time then I multiply it by its probability. So I take the value minus the mean, square it, multiply the probability. This formula is on your formula sheet. This formula is on your formula sheet. The standard deviation formula is not on your formula sheet. However, you know that the standard deviation is just the square root of the variance. Okay, but the variance formula is on your formula sheet that you'll get on both parts of your test. And remember, standard deviation is going to measure approximately how much the values of the variable typically, so it's how much the values of our variable typically are varying from that mean or that expected value. Let's go back to our Apgar scores and do another example with those. So here are our Apgar values again. Okay, and so this time our problem is to compute and interpret. Okay, we're looking for a standard deviation of x. So we're calculating and we're interpreting that. Okay, so remember, standard deviation, right, is the square root of our variance for x. So if I'm going to compute this, I'm going to need to calculate my variance. Again, when I show my work, I do not need to do every single one, right? I can do my first value minus my mean, right, squared times the probability that that happens, okay? And I can do that out 3 times, right? 1 minus 8.128, my second value, minus the mean squared times the probability that that happens, plus my third value minus the mean squared times the probability that that happens, plus my last value minus the mean squared times the probability that that happens. And when I add all these up, I'm going to get my variance, and then I need to take the square root of that sum, and I'm going to end up with 1.437 will give me my standard deviation of my Apgar scores. So what that means, if I'm interpreting that in context, that means that my randomly selected baby's Apgar score typically differs from the mean of 8.28 by 1.44 units. Okay, so again, randomly selected baby's Apgar score typically differs from the mean of 8.28 by 1.44 units. We'll do a couple more quick examples. So looking at this one, I've got a large auto dealership keeps track of sales made during each hour of the day. X equals the number of cars sold during the first hour of business on a randomly selected Friday. Based on previous records, the probability distribution of X is as follows. Compute and interpret the mean of X. So I'm looking for, I'm looking for the mean of X, right, which is going to be my value times its probability plus value times probability plus value times probability plus value times probability, right, which is going to give me 1.1. And so what that means is that 1.1 is the average number of cars sold during the first hour of many, many Fridays. So that's my interpretation of the mean. 1.1 is the average number of cars sold during the first hour of many, many Fridays. Now I'm computing and interpreting the standard deviation. So remember, my standard deviation is the square root of my variance. Your variance formula is on your formula chart, but remember, it's your value of x minus your mean squared times the probability of that value point, and we're going to add all of those up. Okay, so we're looking at the sum of all these. That's my variance. Okay, so when I add all those up and I take the square root, I get 0.943. If you are unsure how, like the order of operations of that, you're going to need to ask. But I don't really have room to write it all out here on the screen. So what that means is on a randomly selected Friday, the average number of cars sold typically varies from the mean of 1.1 by about 9.43 cars. Again, my average number of cars sold on a randomly selected Friday typically varies from the mean of 1.1 by about 0.943 cars. So we spent a lot of time looking at a discrete random variable, but what if it's continuous? Remember, if it's continuous, my sample space is the entire interval. And for example, if I was asking about any random number between 0 and 1, my sample space is all of those numbers between 0 and 1. We're talking from 0.1 to 0.87254613498. My value for capital Y here is going to be my outcome of my random number generator. Okay, so what we're going to be looking for when we're doing continuous random variables is that we're going to be looking at probabilities of intervals of outcomes, not to an individual outcome. It cannot, for a continuous random variable, you cannot assign a probability to an individual outcome. Because when you find these probabilities, you're going to use a density curve, and that density curve is going to have a uniform distribution. And remember, our uniform distribution looks like this. So I've got a curve here with a height of 1. Okay, so let's just kind of give you some help there. Okay, with a height of 1, and then let's take this over here to 1. So this spot here we got 0.5. So this is my density curve here. So it's a uniform density curve. So if I'm trying to find the probability that I'm going to get between 0.3 and 0.7, okay, so an interval of outcomes, not one individual outcome, I can use my area under the curve, right? And so I'd be looking for this area right here. And this area right here is going to be equal to 0.4, right? I have a height of 1, right? Remember, area, length times width. So I have a height of 1, okay? It's 0.4. So 1 times 0.4 equals 0.4. That gives my area. And this is why I can't find an individual area, right? If I wanted an individual outcome, if I wanted the probability of 0.9, I don't have an area under the curve. It's just a straight line there. So I can't do an individual outcome here. But I can use my density curve with a uniform distribution here to help me get that interval of outcomes. Okay, so let's look at an example with this. So we're going to use a 3-step method to solve these problems. So our example here is looking at women's height. The heights of young women closely follow the normal distribution with a mean of 64 inches and standard deviation of 2.7 inches. This is the distribution for a large set of data. Now choose one young woman at random. Call her height Y. If we repeat the random choice very many times, the distribution of values of Y is the same normal distribution that describes the height of all young women. Find the probability that the chosen woman is between 68 and 70 inches tall. So our problem here is the probability that a randomly chosen woman has a height between 68 and 70 inches. We're going to use a 3-step method here to work on these problems, okay, to solve these problems. So the first thing we need to do is state our distribution and our values of interest. Okay, so our distribution here is the height of Y of a randomly selected woman has a, so height of Y of randomly selected woman, you got the rest right, selectively woman, has a normal, why is my end not working? Normal distribution of 64, 2.7, right, which gives me the mean and the standard deviation. has a normal distribution of 64 and 2.7. And your parameters that you want, your values of interest here that I'm establishing are that 68, that y is greater than or equal to 68, but less than or equal to 70. So that's step one. Okay, I state my distribution. So the height of a normally, of a height y, of a randomly selected woman has a normal distribution of 64, 2.7. Okay, and these are my values of interest up here. Okay, my probability that I'm looking for. I can also go ahead and sketch this out if I would like. So when I go ahead and sketch this out, remember it says it's a normal distribution. So this is going to look like, right, my distribution curve. So I've got my normal distribution curve there, right? I've got 64. Okay, I'm looking for the area here, right, from 68 to 70. I want to know what that area there is equal to. Okay, so step 2 is performing my calculations and showing my work. I can do that with technology or I can do that without. Okay, remember I can do this with z-scores. So I can go through and I can show my work with z-scores. So 68 minus 64 over 2.7, and I get a z-score of 1.48. And then my second z-score of 70 minus 64 over 2.7. You need to let them know that these are our z-scores, okay, which is 2.22. So then I can use my table, right, my probability that z is less than or equal to 2.22, which is 0.9868. Remember, my z-scores on my table show me everything to the left of my curve, the left of my point that I'm looking for, right? The probability that z is less than or equal to 1.48, is going to be 0.9306. And so then when I put the probability of 1.48 z here, 2.22, right, I get the probability of 0.9868 minus 0.9306, which gives me 0.0562. So I can do it with z-scores without technology, or I can get out my calculator, okay, and I can use my calculator. I'd still want to draw my normal distribution, 64, 68, 70. I want to know what that area is. Okay, and then I can use my calculator technology, right? But to show my work, remember I need to write normal CDF. Oh, where's my eraser? Normal CDF. I need to define all my stuff, right? My upper is 70. My lower is 68. My mean is, what is my mean in this case? 64. And then my standard deviation is 2.7. So I need to make sure I've identified what all those numbers mean. These are supposed to be, these should be colons in between each new thing you're identifying. There should be a colon there. So I can run that through. I can punch that into my calculator and it will spit out that for me, but I've got to make sure I've identified everything that I put down in my calculator. And then, so that's step 2. So I perform my calculations and shown my work, and then I need to actually answer the question. Okay, and so to actually answer the question here, I'm going to, basically that means my context, right? This is where I put it in context. So what this tells me is that I have about a 5.6% chance that a randomly chosen woman has a height between 68 and 70 inches. Again, so when I'm putting this in context, I have about a 5.6% chance that a randomly chosen woman will have a height between 68 and 70 inches. Okay, and that's our discrete versus continuous random variables.